This story in your textbook talks a little bit about the discrepancy between the calculations you might make in your pre-lab and the measurements you actually make in the lab. So if you're going into the lab and you're trying to build this series RLC circuit and you want to measure its resonant frequency, quality factor, and bandwidth, the way to do that is to first calculate what it might be and then to do a sweep of frequencies. Remember, you're going to get your maximum voltage response or in this case our current response, so our voltage response across this resistor at resonance. So if we were to measure the voltage across this resistor where the maximum voltage response would occur, that would be our resonant frequency. So we calculate that to be 1125 hertz, but our measurements in lab found it to be a kilohertz. So how do we get to the bandwidth? The bandwidth, those are our half power frequencies. We want to change keep our function generator at the same amplitude, but sweep the frequency until we get to a voltage that's 1 over square root of 2 times that maximum voltage, that frequency less than 1,000 kilohertz and a frequency greater than 1,000 kilohertz. So that's how we can get the bandwidth. And then from that we can calculate the quality factor. So our calculations before lab, we just calculate our resonant frequency 1 over 2 pi times square root of LC. Our quality factor, since it's a series RLC, we'll use that omega naught calculation, L over R, and we get 7.071, where in lab we find it to be 0.625. And the bandwidth, the ratio between the frequency in hertz and the quality factor, we calculate to be approximately 160 hertz, but in the lab we find it to be 1600 hertz. So let's look at why that in fact might be the case. For one, we have to measure each of our elements, right? So when we go to measure our elements with a bridge meter, like we've done in lab, we find that this 20 ohm resistor is actually only 18 ohms. At 1000 hertz, we find that this inductor is 21.4 millihenries with a quality factor of 1.2. And our capacitor, which is nominally 1 microfarad, is 1.41 microfarads with 1 over Q, or a dissipation factor, of 0.123. And again, that's at 1000 hertz. That depends upon the frequency. So if we use our formula for our quality factor for a series circuit, that's the magnitude of the series reactance divided by the resistance, then we can find the series resistance for our inductor and our capacitor that are associated with also with their capacitance and inductance to quantify the losses there. So for our inductor, that's going to be our 2 pi 1000, that's omega naught. Our L, 20 times 10 to the negative 3, we get that series divided by the series resistance, we get that to be 112 ohms. And for our capacitor, we get that to be our 1 over our series reactance for the capacitor is 1 over omega naught C. So we get that to be our 13.9 ohms. So then we can model that then in our circuit, and this is what we can then analyze. But we also have to consider the series resistance of the function generator. That's going to make a difference because it's going to change the current that's being driven, as well as our quality factor. So here's the circuit that we need to analyze then. So once we make those adjustments, we can analyze this circuit. Analyzing this circuit, we calculate our resonant frequency to be 916.23 hertz, closer than what we measured as 1000 hertz, but a little bit under. Our quality factor comes out close to our measurement in lab in terms of calculations is 0.684, and our bandwidth, F naught divided by our quality factor, is what we'd calculate, 1.339 kilohertz. What we could measure in lab is the bandwidth. If we measured it to be 1600 hertz, and we measured that's the half power bandwidth, where we measured the voltage response to be 1 over square root of 2 times the maximum, We found the maximum at 1000 hertz. Then from that we calculate the quality factor is F0 divided by the bandwidth. So we still have error. So where does that error come from? Remember, this series resistances in our inductor and capacitor do depend on frequency. So depending upon the quality of the materials that they're made of, that could change as we're going to these half power bandwidths. So there's other elements that could cause that error. So as Dr. Abel says, when using real devices, watch the models that you choose, think well before you calculate, and mind your Z's and your Q's.